This is Chapter 7, the normal distribution, and today we'll be looking at Section 7.1, the standard normal curve. This is a bit of a break from what we were studying the last few times where we were looking at discrete distributions. Now we're going to be looking at a continuous distribution, namely the normal distribution, and we're going to be pretty much focusing on this for most of the rest of the semester. Now the normal distribution is likely the most famous distribution. Even if you haven't heard the term before, you've certainly seen the normal distribution, even if you didn't know that was the name of it. It's this basic idea. The basic idea of it is that it's a symmetric distribution. Most of the data tends to huddle around the mean, with few, if any, outliers, unimodal, all that stuff. Now remember, the way that we want to think of the graph of the normal distribution is that if you remember back in the day when we were coming up with histograms, they would be frequency charts or relative frequency charts, and we would make the x-axis the classes of outcomes, and the y-axis the frequency, or I'll just put relative in parentheses, because it could be the relative frequency of each outcome. Right, and in particular, you didn't spend a ton of time on this, but you could have discrete histograms, right, where each value, right, each outcome was its own bar, right, had its own bar to it. Well, imagine that for the real numbers, where every single possible real number has its own little infinitely thin bar, right? It's not discrete, it's continuous, and so we wouldn't draw a ton of thin little bars like this. No, we would just draw a continuous curve like that, right? Because there are infinitely many outcomes that can't even be listed. The real numbers are actually uncountable. So anyway, the result is a bell-shaped curve, which again looks like this, and it has the following properties. It is unimodal, meaning it has only one mode, right? It's right here, that's the mode. It is symmetric. This curve is this distribution is symmetric about the mode, right? Meaning this half is the same as that half. The mean, median, and mode are all equal, so the center is both at the 50% mark, and it's also the mean, and it's also the median, and it's also the mode. It is infinitely wide, which means the domain of the curve is technically negative infinity to infinity, although, as you can tell, most of the values are close to mu. But technically speaking, every value in theory has some kind of relative frequency. It's just infinitesimally small, basically. And of course it is adherent to the empirical rule, which we've already seen before, but just as a recap, it means the following. I'll use red, green, and blue for this. It's the 68%, 95%, 99.7% rule, which means that 68% of the data is within one standard deviation of the mean, or I'll just use brackets, right? Mu minus sigma to mu plus sigma, which means, right, maybe that's like this amount, right? This is mu minus sigma, this is mu plus sigma, right? And so then this right here is 68% of the data. Okay? And then similarly, 95% of the data is within mu minus 2 sigma to mu plus 2 sigma. And I'll just write this other one, I'll draw them both. 99.7% of the data is within mu minus 3 sigma to mu plus 3 sigma. So just to illustrate these guys, All right, we've got, like, I don't know, something like this, which is mu. Like, that seems a little bit far away. Like, maybe something like this, mu minus 2 sigma to mu plus 2 sigma. And then the blue would be, like, here or something, right? Mu minus 3 sigma to mu plus 3 sigma, right? And the idea is that this, or maybe I'll just do, like, between this and this all right here, or maybe I'll use a green highlighter to illustrate, right? This right here is 95% of the data. And then I guess if we use a blue highlighter, right, to get all of that too, that right there is 99.7% of the data. Okay? Now, since the normal curve is the graph of frequency distribution, we can use the curve to infer proportions of a population, just like we can with other graphs. So, for example, consider the following graph. Oh, it went away, but let me just quickly sketch it. It looks something like this. So, there's the x-axis, right? The y-axis is always frequency. This isn't even a normal curve, but suppose that we had a graph like this, and suppose the area underneath this section right here was 0.16. You could say, what does the shaded area represent? Well, you could say, and then, well, I guess we'll shade it, right? And we could say the shaded area represents 16% or 0.16 of the population. I.e., 16% of the population, I guess you could say, has, I'll just say variable values between, if we call this guy A and B, or maybe I won't even say between, I'll just say in the interval from A to B. Okay? And again, this is just true in general. And the assumption that we make here is that the total area under the curve is 1. That is just our definition. We assume that that area equals 1. Okay. Now, if you remember when we looked at the binomial distribution, that was completely determined by the number of trials and the probability of success. So I wrote something like B of n comma p. Remember that? Well, similarly, the normal curve is determined entirely by its mean and its standard deviation. So we can accurately estimate proportions of populations just by knowing mu and sigma. Okay. So what we do is we can take each raw score, x, translate it into its z-score. Now recall the z-score formula. Z equals x, right, the raw score, minus the mean divided by the standard deviation. And that is the number of standard deviations x is away from the mean. Okay? Let's write that down here. Or I should say is above the mean. Right? Now, alternatively, you might see the z-score being written like this. X minus x bar all over s. This is just a question of whether it's population data or sample data. They both numerically mean the same thing. So when you do that, let's take a look at what happens here. We can go and get out Desmos here. And if we just take a look, and we just open up our normal curve, right? See, here's again that 68, 95, 99.7 rule, right? Now let's see what happens. When we take every point, we translate into its z-score. Well, let's think what happens. Well, what's the z-score of the mean? It's 0, right? Because the mean is 0 standard deviations above itself. And if you notice, the blue region, that's the stuff that's 1 standard deviation away from the mean. Well, if we want that to be 67% of the graph, then we just set s equal to 1 in this case. And we have this guy. Okay? And so we have this thing called the standard normal curve. Let me actually try to move it up like this, just so I can get this here. I'm going to crop this photo right here. If we do this, we get the there we go. We have the standard normal curve. The standard normal curve, right? So that's what this is, right? That guy right there, okay? And the values on the x-score and the x-axis are z-scores. The standard normal curve has mean 0 and standard deviation 1. And if you notice, most of the values on the standard normal curve are between between -3 and, I guess it got cut off a little bit, but this right here is 3. Right? So that's one very nice thing, is you can just take whatever data set you want and just take all of it, and if it's roughly normally distributed, then roughly 99.7% of the data will be between -3 and 3 on the standard normal curve. All right? So if we consider the following standard normal curves, then what proportion of the population are within the standard shaded regions? Well, do you see what this is really saying is what proportion of the population is less than 1.25 standard deviations above the mean? Less than or equal to, right? Well, to answer this, we can go and get out our Excel file, and we can go to normal, no x find prob, and we get, so let's see, if we put in a mean of 0 and a standard deviation of 1, right, because we are talking about standard normal curve. Oh, actually, you know what? Note that since this right here is the left tail, right, the blue is to the left of the z-score, we put in, we look at the left tail situation, and we say known value of x naught, and we put in 1.25. And you see we get 0.8944. Let me just kind of crop that out a little bit there. All right, you see? So we have that little Excel thing right there. So that answers part A. Okay. Now for part B, what percent of the data is above, or I guess equal to, 0.36 standard deviations above the mean? Well, we do the same thing, except we're going to use the right tail. Okay? So for this, we're going to put 0.36, again, making sure that our mean is 0 and standard deviation is 1. And look, we get this as our answer. let's just paste that in there. Right, so just to be clear, our answer for this one is 0.8944 of the data has z-score at most 1.25. Here, 0.3594 of the data has at most, has z-score at least, I should say, at least 0.36. Okay. Now we can also go backwards, right? We could also say find the z-score in the 80th percentile of the standard normal curve. So what that means is we're looking for the z-score that corresponds to this. Right, there's our z-score that's unknown, and we want this to be 80%. So what we do is we just go to Excel. We go to normal, no probability, find x, right? So we did have to switch worksheets. We again make sure our mean is 0, our standard deviation is 1, and I guess in this case we're going to want the left tail, right? The known probability, we don't want it to be 0.08, just maybe 0.8. And that's what we get, 0.416. So we could say z equals 0.8416 is the 80th percentile of the standard normal curve. And we can just do this similarly if we want to find the proportion between two z-scores, right? Maybe it's at least this and at most that, right? Now let's see if Excel lets us do that. So what did we say before? It was negative 0.34. What was the other one? 1.12? All right, so this is going to give us the sort of opposite. Well, actually, no, I guess not. It does have the answer. You just have to sort of look for it right here, right? So you see how right here it says the probability that x is between x1 and x2? That's our answer. So there it is, right there. Just lower it real quick. Just sort of crop this. Right, so we have that right there. So we would say 0.5017 of the data has z-score between negative 0.34 and 1.12. And then last but not least, we could just ask this kind of problem, right? Find the z-score such that 72% of the area in the standard number curve is between negative z and z. And here's another one where we know we know the probability, right? We're given the probability, and we have to find the z-scores, right? So here's the one we go here, right? We switch from this workbook to that workbook, or sheet to that worksheet. And so the known probability is 0.72. Oh, wait, hold on a sec. Yeah, let's try that point. Not quite what we want. Let's see. The probability that x... So I guess we have to do a little bit of math in this case, right? If we want the z-score such that 72% of the data is between them. And let's just draw a picture first, right? Well, a little bit of a better curve than that. We would need something like this. We want negative z to z, right? And of course, this is 0 right here, where this region right here is 72%. Okay? So let's see how that corresponds to the Excel file. The probability that x is less than x1 or greater than x2. Let me actually go back to the picture one more second. Just to point out, that means that this right here is going to be what? This right here is going to be 100% minus 72%, which equals 28%. Which means because the curve is symmetric, there's going to be 14% here, 14% there. So if we go back to Excel, we're going to say the probability that x is less than x1 is 0.14. Probability x is bigger than x2 is also 0.14. And we have that. So you see how 0.72 is right in between? That's exactly what we were looking for. And we're just going to stick this in here. All right. And so we would just say z equals 1.0803. And that's what we've got.